Pardon me? Oh yeah. Oh yeah, anything for the test is good. Anything you want. Let's just go find that page, which would be over here, I think. Yes, there it is. Okay. What do we got? Anyone? Yes. Yep, yep. In the book, okay. Okay, yeah. Yes. On page 80. Page 80? Okay. Shh. I cannot hear her. I still cannot hear her. What are you guys doing? Okay, you had a small amount of NaOH, yes? But why? Because of this reaction here. So the OH minus grabs the H3O plus, and actually there should be a 2 H2O here, but it turns the H3O plus into water. So there will be less H3O plus than before. Does that make sense? Yeah, well, I mean, this is the reaction that's happening here. It will be like this plus OH minus, and then this will turn into H2O, which means you have less of this. It'll shift to the right, yeah. Yeah? Cool, cool. Anything else? Just a second. Yes? 3 on the written, yes. Keita, yes. Yes. I think I need to print out another one. I don't know what I did with my stack of them. They are somewhere in the universe. Okay, hang on a second. Okay, quiz. Yeah. 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 File. Print. 338. Print. Huh? No, we're learning new stuff. But apparently everyone's like, I'm not going to be here. I don't know. People make choices. We're having a quiz on this stuff next week, so I don't know why people would not be here. It's crazy to me, but whatever. We make choices in the world. Yes, we do. Stay there. I mean, wants to. What? Data booklet. And it will make no difference to this time, but if you have a job, you need to arrive on time so you don't take everybody else's time. Right? Because like everybody's waiting for you. Yes? Yeah. Hi, and you also, right? Because now everybody's waiting while I give you your quiz. There you go. Okay. So where were we at? And if everybody's wondering, all the teachers are grumpy right now because we're all doing a million things. And to be fair, like I said, I'm probably not grumpy at most of you because most of you are the people who are here every day. But yeah, I was just talking with Ms. Riley and she's like, you know what? She was telling a student, she's like, this is not a drop-in class, right? And I'm like, no, it's not. You don't have a flex pass to this class. It's not like just drop in at the gym whenever you want to. It's bizarre. Hi. Okay. Back to those of you who are here and who are asking me questions relevant to the course. Thank you for being with it and everything. What would you like to know? I'm sorry. Number 3 on the written, yes? Okay, cool. Where did you go? No? Okay. Calculate the pH of a solution made by dissolving RBOH in HNO3. Assume no volume change. So what we've got here is we have a situation where we have a base. Rubidium, by the way, is what type of a metal? It's alkali, so it is completely soluble. So what you're going to do is you are going to find moles of RBOH. You are going to find moles of HNO3. And do you know what to do when you find moles of an acid and moles of a base and you would like to know what the pH is of the mixture? Do you? Maybe? Maybe? You're going to write the reaction. And it's a strong. What's the reaction? H plus OH minus gives H2O. And what tool can we use here? A RICFA table. Now, I don't know what these numbers are. Like, you can turn grams into moles, yes. And you can turn this into moles. You just have to be careful that you're working either in moles or millimoles. You'll have to convert one of them. Doesn't matter which one. And then let's just call this X and let's call this Y. So we would have X and we would have Y. Whichever one is smaller would be the one that we subtract. And then it would be in a final volume of 79.8 milliliters. Do you want me to go through the whole thing or we're good? Okay, very cool, very cool. Other questions? Yes? You can use it in molarity, yeah. I've only shown one method of using it, so yeah. But yes, absolutely you can. Yeah. Anything else? 7 on the written. Okay. Seven on the written. Oh yeah, you don't need to know that one. That's acid rain. That's part of 5.7. Okay, so anything acid rain or anhydrides or oxides, don't worry about it. Okay? Not unless you're not planning on taking the test tomorrow, in which case you get to learn that for Monday on your own. Is that thing making noise? What? Is it my... Oh! I'm like, where is that noise coming from? Oh my God. That's so bizarre. Anyway, no, I was listening to something in the car on the way here, and then I guess I didn't turn it off properly, and it was quite low, so I didn't hear it with all the commotion, and now I'm like, there's this man mumbling in the background. Okay, anything else? Alrighty then. Let us go to our new workbook. And we had just finished looking at oxidizing agents and reducing agents. And now we are going to look at simple half reactions. The answer key's over there as well. This is on page 10. And remember, these reactions are called redox. Why are they called redox? Because they involve both reduction and what's the other process? Oxidation. And how can you remember what's happening in oxidation? And what's happening in reduction? Leo the lion says, grr. And so that stands for, what does the L stand for?
Loss of electron oxidation.
Losing or loss of electrons is oxidation, LEO, and gaining electrons is reduction. All right, so losing electrons is oxidation, gaining electrons is reduction, and we are going to be looking at the half reactions, which is where we split the redox reaction into halves and look at each half individually. Okay, so last day we looked at an oxidation half reaction. How can you tell which of these two is the oxidation half reaction? Don't look at your book because it just tells you. But which one, like, how can you tell? We're going to look at the electrons. The electrons, in this case, the electrons are coming out. And if they're coming out, are they being gained or are they being lost? They're being lost. Therefore, what is happening to Na? Na is being oxidized. And I've put a little 0 up there because remember, if you have no charge, you have a charge of 0, okay? So electrons are being lost, therefore Na0 is being oxidized. How else could you tell that sodium is being oxidized? You can look at where the electrons are. If they're coming out, it's oxidation. What else could you look at? You could look at the charge, or we're going to start calling it the oxidation number, although you'll notice I often call it charge because it's just easier sometimes, because that's what we are used to thinking of it as. It has changed from an oxidation number of 0, and it has changed to an oxidation number of +1. And remember, oxidation number needs the plus and the 1. And so something is oxidized if its oxidation number gets bigger. So the oxidation number increases, that is oxidation. All right, and yesterday we just looked at Cl gaining an electron, but Cl doesn't come as just chlorine atoms, it comes as Cl2. So you would actually have each chlorine atom going, what's the charge of chlorine in Cl2? What's the charge of chlorine in Cl2? 0. So chlorine goes from an oxidation number of 0 to an oxidation number of, what is it over here? -1. And don't worry, just because you have 2 of them does not change the oxidation number. The oxidation number is just on a single atom. Okay, so that's what we look at, is what's happening in a single atom. So you could say either I can see that electrons are going in, and therefore if electrons are going in, what's happening? Are we losing or are we gaining? Therefore we're gaining electrons. And therefore Cl is being reduced. Because Leo the lion says gaining electrons is reduction. Leo the lion says grr. You can also tell because what happened to our oxidation number? Our oxidation number went from 0 to -1. The oxidation number, did it go up or down? It went down. So the oxidation number was reduced. Therefore, it was reduction. Now, if you were away yesterday, you've caught up on half the lesson. Okay. So if the electrons are in the products, you have an oxidation half reaction. And if you have a reduction half reaction, the electrons are in the reactants. In nature, half reactions cannot exist in isolation from each other, but we tend to look at them in theoretical chemistry a lot by themselves. So on paper, we might write these various reactions. Could you please identify each of these as either an oxidation or a reduction half reaction? A is, everyone, oxidation. B is reduction. And C is oxidation. And you can see that this one here, this one's easy to see. The oxidation number went up, so it was oxidized. In this case, we went from 2 to 0, so the oxidation number went down. I'm just adding that on. I assume you got it from the electrons because that's the easy way to do it for these ones. And then for this one here, who is being oxidized and who is being reduced, and how do we know? Like, we know it's an oxidation because we have the electrons coming out there. But if you wanted to, you could look at the oxidation numbers. What is the oxidation number? And you can almost always assume that if there's oxygen and hydrogen, it's not them, it's the other guy. Okay? Oxygen and hydrogen are probably not being oxidized or reduced. It's probably the other guy. So it's probably I. What is the oxidation number of I in I2? 0. And we often write it in a little circle above the numbers. Now, again, quick review from yesterday. Let us calculate the oxidation number of I in iO3 minus. So just to review, and for people who weren't here, what we do is that we take one I, because we've got one I in the formula, we add it to 3 O's, because we have 3 O's in the formula, and that is equal to the overall charge, which sometimes is 0, but in this case it is -1. We are trying to find the oxidation number, which is kind of like a charge for the iodine, so we're just going to leave that as 1I. And then we're going to replace the charge of oxygen in for O. What is the charge of oxygen? -2. And if you were away yesterday, there's a list of rules in the previous section on that. Okay, so we've got equals -1, and then to just, grind through the algebra a little bit pedantically here, we've got 1I minus 6 equals -1, and so I is equal to +5. So we have an oxidation number for the I of +5. And that confirms this number got bigger, so that got oxidized. Not that you would have to do that, but I thought it was a good opportunity to review that skill from yesterday. Okay. Half reactions are important for balancing redox reactions. If you came across some reactions last year in Chem 11 and you're like, how on earth does anybody balance this? This is crazy. This is a manic, nutsy equation. I have no idea how anybody does it. It was probably a redox reaction, and we have special ways of balancing them that will save you headaches and heartaches, okay? So if you have an overall redox reaction, what you will do is you will start by writing the net ionic equation, if it's not already given to you as a net ionic equation. In other words, get rid of the spectators, because they're just going to confuse you and mess you up. You are going to separate the two half reactions. And you're going to, doing this on simple reactions is really easy, but it's going to show you how to do it in more complicated circumstances. So bear with me while we do this in an easy circumstance. Once you have your half reactions, you add electrons to the correct side of each half reaction to balance the charge. And so you will see that one of your half reactions will be oxidation and the electrons will go in the products, and one of your half reactions will be reduction and the electrons will go in the reactants. We're not going to watch the copper foil demonstration, but basically what we have is, I'll probably do it next week so you can see it, but I feel like we have no time today, so we won't do it today. Basically, you've got solid aluminum. So can you imagine some solid aluminum getting crumpled up and thrown into some aqueous copper sulfate? So it's like a blue liquid with the copper 2 ions floating around, right? So this is aqueous here. All right, and the aluminum is solid. And then that turns into copper solid. That's where I got my copper from. Where did my copper go? I don't know. That's okay. So at any rate, we're going to write the net ionic equation. So you can do that by writing the complete ionic equation. The CuCl2 will split apart into 3 Cu2 plus and 6 Cl minus. The aluminum chloride will split apart into 2 aluminum 3 plus and 6 chlorides. Are we okay with where those coefficients came from? Okay, good. And then we look and we say, who are our spectator ions? Spectator ions, we've got chloride and we have chloride. Remember, you cannot cancel neutral aluminum with aluminum 3 plus. Those are different things, okay? You can only cancel things where the substance and the charge are identical. So we are left with 2Als plus 3 Cu2 plus gives 2Al3 plus 3 Cu solid. So we're going to say we've got 2 half reactions. So you're going to say, what is aluminum turning into? Als is turning into Al3 plus. So this is very much like finding the conjugate acid-base pair, okay? And Cu2 plus is turning into Cu, okay? Can you see which one is the oxidation and which one is the reduction? Aluminum is getting, tell your partner. Is aluminum getting oxidized or reduced? The oxidation number went up from 0 to 3, and therefore it was oxidation. Copper went from 2 plus to 0, so the oxidation number reduced, therefore it is reduction. All right, now we're going to separate this into the 2 half reactions. We're going to take the aluminum and write it separately from the copper going to copper. Now, when we have these here, we can simplify that and get rid of those coefficients, and our half reaction becomes Al goes to Al3 plus. So far, so good? Okay. We have 3Cu and 3Cu. That goes to Cu2 plus and Cu. So those are our half reactions. Where would you put the electrons in aluminum to balance the charge? Electrons are negative. Would you put them over here, or would you put them over here? You would put the electrons on the right. How many electrons would you put on the right? The charge on the left-hand side is 0, so we need to make the charge on the right-hand side also equal to 0. So how many electrons would we need? 3 electrons. And that confirms for us that, hey, those electrons came out. That's a loss of electrons. Is oxidation. LEO. Leo says Gur. Copper 2 plus goes to copper. Where would we put our electrons for that one? We would put them on the left side, 2 electrons there, right? Because that's going to give us 2 negative and 2 positive, gives us 0, which makes same as 0 over there. Okay. And we can see we've got that here, notice the overall charge has to be balanced. This is on our next page where it says the note. We already did the part at the top. So our little note there. The overall charge on each side has to be balanced, but it does not have to equal 0. So if you had Fe2 plus on the left and Fe3 plus on the right, you would balance the charge by adding 1 electron here so that each side is equal to positive 2. Okay? Okay. We're going to, I don't know why I didn't do this here. Let's take our aluminum and let's put it with our copper. If aluminum is trying to give away 3 electrons and copper is trying to take 2 electrons, is that going to work out nicely? No. So what we're going to do is we're going to take that top equation. What should we multiply it by? We should multiply it by 2. That's going to give us 6 electrons. What should we multiply the bottom equation by? 3. And so what you'll end up with then is 2Al goes to Al3 plus, 2Al3 plus, plus 2 times 3 is 6 electrons. And then we have 3 copper 2 plus 6 electrons goes to 3 Cu2 plus. And if we add those two up, I shouldn't have drawn my line like that, but that's okay. I'll fix that. Try that again. There we go. Okay. We end up with, is there anything that cancels out? Anything that's on both sides that cancels out? Yes. What cancels out? The 6 electrons. Yes. Okay. So we've got our 6 electrons. This pen has conked out on me. Grab this one. And then we end up just adding everything together like we did in A. So everything on the left-hand side goes on the left-hand side. So we end up with 3 Cu2 plus 2 Al goes to 2 Al3 plus 3 Cu2 plus. And we now have a balanced reaction, as we should, because basically we've just we took it apart and we unbalanced it and then we rebalanced it. Okay, so this one is a little bit, I don't know, it's kind of weird to take it apart and then go backwards, but yes. Because Ms. Spence does not know what she's doing. There we go. Let's get rid of that. There. And you can always check and say, do I have the same amount of charge on each side? If I was to have checked that, I would have ended up with way more positive on the right than I did on the left, and I would know that I had made some silly error somewhere. Okay? So what you should have is we have 6 positive on the left, and we have 6 positive on the right. That's a quick way of checking to see if you've balanced things, is to see if the charge was balanced. Okay? All right. Let us try another example. And I'm actually going to do this off to the side. If you want to grab a piece of paper and do it along with me, you can. And in fact, you know what I'm going to do? I'm going to get rid of these 2's. Let's get rid of these 2's. Let's make this a fully unbalanced redox reaction. Okay, it would be really easy just to balance this. But let's do it. This is an unbalanced redox reaction. First thing you need to do is you want the net ionic equation. So we're going to have F2 stays as F2. KCl splits apart into K plus and Cl minus. Kf splits apart into K plus and F minus. And Cl, those are aqueous, aqueous, and Cl2 stays together. Any spectator ions for us to get rid of? Okay. And that's it for today. Study hard for your test tomorrow. And I'll assign some stuff from yesterday for homework for the weekends. Okay? Yes. Oh, this one.